Hello friends, Mr. Burrell here. Sorry my camera's being kind of weird today. But we've been talking about graphing, we've been talking about parent functions, we've been talking about transformations. In our last video we talked about horizontal and vertical transformations. So we're going to extend that a little bit today with other types of transformations that you might see in a function. So hopefully by the end of today you're able to identify transformations that have been applied to a graph and graph a transformed function. We kind of feel comfortable with doing that with our vertical and horizontal shifts, those transformations already. So hopefully now we can start to learn to be comfortable with these other sorts of transformations. So if you have guided notes from me, there's a page, I think it's page 8 there, that looks something like this. If not, I'd recommend you writing down these functions because we're going to be graphing them. We're going to follow the same pattern we followed in my last video. There are 6 different functions here. They have the parent function and then a function that has been altered or transformed. So what we're going to do, we're going to graph them and we're going to see what we notice. We're going to take note of what changed. So I'm going to go out of here for a minute and we're going to come into my Desmos graph here. So the very first function that we're looking at is y equals x squared. It's a quadratic function. That's the parent function. It crosses right here through 0, 0. So I want you to take note, what do you think is going to happen when I type in y equals negative x squared? What's going to change? How is it going to be affected? Take a second, think about that, and I'll show you here. That negative x squared ends up making this graph flip or reflect over the x-axis. Kind of just flips upside down. See that? So this negative here affected this graph by flipping it upside down or reflecting it over the x-axis. Okay, take note of that. Here's my function y equals x cubed. This is my regular parent function, my squiggly noodle function, some of us like to call it. How do you think it's going to be affected if I type in 3x cubed? What do you think is going to change? So notice here, it didn't shift left or right, up or down at all. It still passes through 0, 0, but it's kind of squished in. It's almost like I took the top and the bottom of this graph and I stretched them out like that. See that? Okay, we might notice something very similar that happens with this square root function. So here's the y equals the square root of x. What do you think might happen if I type in 4 times the square root of x? Let's see. Again, it kind of looks like I was stretched out, like I grabbed the top of this function and stretched it up into the ceiling. A little bit steeper slope, a little bit skinnier maybe. So that's what happens when I put a 4 in front of the square root of x. Let's look at the absolute value of x. So there's my parent function. This big, broad V is what that looks like. What do you think is going to happen when I type in 1/4 times the absolute value of x? What's going to happen here? So instead of this V kind of like this, it kind of flattens out, almost like I'm opening a book. So instead of like stretching it up, it's almost like I'm pushing on the top of this V and kind of flattening it out, compressing it a little bit, if you will. Okay, so take note of that. Here I have y equals x squared, another quadratic graph, my parent quadratic graph, my little U shape. What do you think is going to happen when I type in negative 5x squared? What do you think? So you notice negative kind of made it flip over upside down, so it looks like this instead, an upside down U. And this 5, again, made it go a little bit skinnier. So almost, again, like I grabbed the bottom of this and I kind of stretched it out. Last, but certainly not least, let's look at the square root function again. I have y equals the square root of x. And you'll notice I'm combining some of our new transformations from today with some of the transformations we've already done. So if I ignored this negative for a minute, you can see the square root of x minus 3 plus 2 inside the square root affects my left to right, so it looks like that's going to move to the right 3 spaces. Outside the square root moves up and down, so that looks like it's going to move up 2 places. And now this negative is going to make it flip. It's going to be upside down. So notice what happens here when I click on this graph. So it's flipped upside down and then moved to the right. Let me see if I can. Yes, to the right 3 units and up 2 units. See that? See what happened there? Okay, so I want you to take all of those things into account. We're going to go back here into my slide. Here are all these different types of functions that we've discussed. Yesterday I had x minus h squared plus k, x minus h cubed plus k, the square root of x minus h plus k, the absolute value of x minus h plus k, etc., etc., etc. Now, in addition to that, I have this a at the very beginning. So you notice in the graphs that I just graphed, there was a number at the very beginning, whether it was 3 or 4 or 1/4 or -5. I want you to think, I want you to make a conjecture. There's that word again. I want you to make a conjecture. What do you think A has to do to the graph? How does A affect the graph? Think to yourself for a minute. You might be thinking of a lot of things. But we're going to specifically identify a mathematical way to identify how A affects these graphs. So, if A is greater than 1, so like 3 or 4 or 5 or 17 or 132, if A is greater than 1, that's going to cause a vertical stretch. So you notice I kind of, when we were looking at the cubic function and at one of the square root function, or the square root and the quadratic functions, it looked like when I had a number in front of there that I kind of had taken the top and the bottom and kind of stretched it out. Almost like I'm stretching Play-Doh or like silly putty or something. Kind of stretches it out, makes it look skinnier. That's going to cause a vertical stretch. If I have an A value between 0 and 1, so like a fraction, for example, 1/2, 1/4, 0.5, some fraction like that, that's going to cause a vertical compression. So almost like I am pushing down on the top and the bottom, kind of flattening it out. If I were to like flatten out some silly putty or Play-Doh, almost make like a pancake type shape. It's flattening it out, compressing. We're going to call that a vertical compression. And then if I have an A value that's less than 0, so if it's negative, if I have a negative value there, that's going to cause a reflection. Specifically, a reflection over the x-axis. So it's going to flip over the x-axis. So I want to show you back in Desmos here kind of what that looks like. If you need to rewind my video and go back to that slide so you can kind of copy those down, that's great. But right down here at the bottom, I'm going to change this back to what I want it to be. I have y equals the absolute value of x, this parent function right here. Y equals the absolute value of x. It's a v. And right now, you notice I have kind of a slider down here that's going to change my a value. Right now it's 1, so this is the parent function. Notice what happens when I make a bigger. Notice what's going to happen. So I'm making a 2, 3, 4, 5. Notice it's almost like I took the top of this graph and I stretched it. I stretched it, kind of made it skinnier, thinned out a little bit. That's a vertical stretch. When A is greater than 1, it causes a vertical stretch. Now if I go back down here to 1, notice what happens to the graph when I put in a decimal. It's like 0.9, 0.7, 0.6. Notice what's happening. That's what I call a vertical compression. It's like I was pushing on the top of the graph and just pushing it down, flattening it out. That's a vertical compression. Now, what happens if I make it negative? So if this was just -1, it's exactly the parent function, but flipped upside down into the negatives right here on the other side of the x-axis. It reflected over the x-axis. And once it's reflected, once it's negative, all these other same rules apply. If it's a number down here that's bigger than 1, it's going to stretch. If it's a number down here that's a decimal between 0 and 1, it's going to compress. So hopefully you can see some of those patterns emerging. I would write down those things that I had in the video just a minute ago, those rules for A. And now I want to kind of fill in this table I have here with these different things. The other day I had a table very much like this. I had a graph column, a parent function column, transformation column, and a transformed function column. So let's fill in these blanks. So this first row, this is a quadratic function with a vertical stretch by a factor of 3 and reflected over the x-axis. So for example, this might be my parent function, quadratic function. If I have a vertical stretch by a factor of 3, it's going to get kind of skinny. I'm going to stretch it out. Then if I reflect it over the x-axis, it's going to be that same skinny quadratic graph, but reflected over the x-axis. So that right there, ignore these, that's what my graph might look like. Not exactly. That's what my graph might look pretty close to. Then if I want to draw the function, I might draw something like this. F of x equals, and this is a quadratic function, so I'm going to have an x squared here. Vertical stretch by a factor of 3 means that there's going to be a 3 in front of here, and reflected over the x-axis means that's going to be negative. Negative 3x squared. That's how I would draw or write the function for this transformation. Let's look at a square root. Here's a square root function, might look like this. Right here, f of x equals 1/2 times the square root of x. Since that a value, the number in front of the square root, is a fraction, that's going to be a vertical compression. So if I wanted to draw this graph a little bit more accurately, maybe it's flattened out a little bit more pancakey. So it's a vertical compression by a factor of 1/2. By a factor of 1/2. So it's being compressed by a factor of 1/2. Next down here I have an absolute value function. This is an absolute value function. I know because it's a v and I have these absolute value bars. So right off the bat, if I'm just ignoring this 2, this transformation I recognize from the last video, the last lesson. This is moving to the right 3 and down 2. And now, in addition to that, I have an a value out here. I have a number in front, so that's going to be a vertical stretch. By what factor? By a factor of 2. So that's how I describe my transformation. A vertical stretch by a factor of 2, moved right 3, down 2. Okay. This last one, this is just a line, so this is a linear function. And if I didn't have a 3 here, this would just be shifted down 4. Since there is a 3 here, I describe that as a vertical stretch by a factor of 3. Factor of 3. Some of you may look at this linear function and recognize that 3 as what the slope of this line would be. So remember, if you remember back to, and this isn't super critical to know, I just like to point it out, if you look back into your math knowledge previously when you're talking about linear functions, they're written in this way, y equals mx plus b, where m is the slope, b is the y-intercept. Notice, I shifted down 4, so there at -4 is my y-intercept. I also stretched, I have a vertical stretch on this, so it's going to change how steep my line is, or how steep the slope is. So the vertical stretch is basically another definition of what the slope of this line is. So saying down 4 vertical stretch factor of 3 is another way of saying a y-intercept of -4 and a slope of 3. So kind of making connections here. I hope those connections are valid. I want you to self-assess yourself. Hopefully you know how to do these things. Hopefully you're able to identify all these different kinds of transformations that have been applied to a graph. If I give you a graph, hopefully you can see those things. If I give you a function, hopefully you would be able to graph an approximate graph of that function using the transformations given. So I hope that was helpful, and I hope you enjoyed that as much as I did.